All right. So over here in Buzz, you have your reading. So you know that your lesson generally goes in this pattern, right? You got your reading, you got your assignment or assignments like this week we've got 2 assignments. So reading, assignment, quiz, and then eventually test. Now, I know you just had a test last week, but we're going to have a test again this week. I'm giving you tests on information that is smaller, so our tests don't have to be so large, right? This actually really helps you get better grades if we don't have tests that are so large. So I know we just had one, but we're having another one. And then we'll go to bonding, and then it'll be a while before we have a test again. All right, so reading, assignment, quiz. That's our pattern. So I also, and so when I surveyed my kids yesterday in class, they indicated that it would help them if we had a Google Classroom, which we do, but if I put the assignments on Google Classroom. So I am not putting the assignments in Google Classroom. What I am doing is putting what assignments are due this week. So all assignments are still in Buzz. That will not change. We need that steady consistency there. But what I am now putting on Google Classroom is just a list of what is due on Buzz for that week. Okay? So there's a list. It'll be there. If you're ever confused about Buzz, don't know what to do, you'll have your list. Now on Buzz, back to Buzz. Okay, everybody seeing Buzz? I never know when I click back and forth if things are going to work right. All right, on Buzz, it's kind of hard to know what's due. If you haven't been keeping up, then it looks like, oh, I've got these 3 things to do and these 4 things to do. Well, these were due earlier, right? And so if you go to your to-do list here, it will show you your due dates, right? Also, if you go to calendar. But people are so used to Google Classroom that they really wanted me to put what our assignments were for the week. So a list of assignments will be in Google Classroom weekly, and then you'll come to Buzz and you will actually do the assignments on Buzz. That will not change. All right. Now, what I am doing a little different, which Chandler was asking me about earlier, is that I am making our assignments on GoFormative. Okay, so what was happening before was I was giving you an assignment, and I was giving you an assignment like I would in class. Like, here, do this worksheet, and then we go over in class. Well, we can't go over in class. I can't bring you into class every time I want to go over a worksheet, right? So, of course, that's what we're doing today, but but that's information, so that's different. But so the first week or so, I gave out assignments, and then y'all gave them back to me, which you're really good at. Very good job. And then I had to grade them, and I had to put comments on every one of them. And so it took me forever. And actually, I'm still not done. But, and then you had a test, which is not good. You need to have feedback from me before you take the test, right? So we are now going to have all our, if I have time, because it takes time to put on GoFormative. But if I put them on GoFormative, you can have instant feedback. Now, Chandler found that not all of them will give you instant feedback. So the ones you have to type in, which really aren't that many, I will have to grade. So once you go do one in GoFormative, let me show you what it will look like. You'll have to click the GoFormative link, and then you'll have to sign in. So the first time you go to GoFormative, now I have already put you in, so there shouldn't be any problem with you signing in. Just sign in with Google. So after the first time you sign in, then you won't have to sign in anymore. Okay, so it's just the first time. And then after that, you should just go straight to your assignment, and it'll look like this. A lot of it's multiple choice, and it's also teaching you. So a lot of what I will put on is models, and it will ask you questions about the models, but it's also teaching you something along the way. Okay, so a lot of it's multiple choice. So once you choose something, you'll know whether it's right or wrong. So you'll get instant feedback, and you won't have to wait for me to grade it, right? So that's great when we have test weeks. You won't have to wait for me to grade it, except for those ones where you have to type in. All right. So instant feedback is the way our assignment's going to go. Everything will be on Buzz, but we may take you to a link on GoFormative. Okay. Any questions? All right. Remember, put your questions over there in chat. All right. One more thing about Buzz, and this is really, oh, I'm sorry. When you're done with your GoFormative, you can hit this submission button right there, and then you could submit your work. And that will tell me in Buzz that you're done. Okay? So now, one more thing in Buzz, and this is really hidden. I had to search for this myself. Let's see, what am I in? Am I teacher or student app? All right. Okay. If I go to my grades, okay. When you go to your grades, you'll see what I've graded here, or what Buzz is graded, because sometimes if you just have a multiple choice, it automatically grades it, right? Buzz does a lot with icons. So if you go to your grades, here are your grades. Here's the status. The check mark means you've done it or looked at it at least. And then you see this circle arrow. That means you can retry. I have set it where you can retry. Now, I have set all of these that you can retry how many ever times you want, but for some reason, it wants me to click that every time. So that doesn't work as well as I had hoped it worked, but so you're probably going to have to ask me when you want to retry, or if you automatically get below a 70, I will automatically retry when I grade it. Now, what I really came here for, that's not what I came here for, to show you. What I came here for is to show you this. This little chat box or thought bubble, or I don't know what else you call it. Okay, click that because you want to see the comments that I put on. Okay. All right, so if I put a comment, it's got the little chat bubble out there. You pull it, you click it, you pull this up, and it's got feedback right here. Now, if I am talking about an assignment, I will probably put a number or a slide, and I'll make the comment on that slide. I now know I need to make the comment on the comments, and I'll put the number or the slide, and then you can click over here to questions to see what you got wrong and what you didn't. And then you can figure out what I was talking about, because I will put the number or whatever. So just so you know how to look at past stuff that you've done, especially when you're retaking a quiz, you want to look at what you did wrong. Yes. Okay, Chandler, did I answer your submitting them a Buzz? The GoFormative, is that what you're talking about?
Whenever you do it, you have to attach something to submit it.
Oh, do you?
Yeah.
Because I really thought.
That's why I couldn't mark the atomic model thing in Buzz, is because you have to attach something in it.
Okay, well, we are all still learning here, are we? Oh, I can't show you that. Okay. Okay, well then don't worry about submitting anything for the GoFormative, because I will grade GoFormative and it'll be fine. So don't worry about that, Bill. Well, you know, I am new to Buzz and I am still learning about it, and sometimes I don't see what you guys see. So I don't know what problems you have on your side. Okay, we're gonna look at that in a minute. Okay. All right, we're gonna get to atomic trends.
Let's do Sunday. 198 is the practice exam and is not counting.
Okay.
You can take it as many times as you
Atomic trends. All right, we're gonna get through this, and then I'm gonna have you do your signature and email, and then we're gonna be done. All right. So I am not going to keep you the entire class period. Woo! All right, atomic trends. So trends are patterns on the periodic table.
I am available for questions.
And there are lots of patterns, and that's what we look at. So when we say trend, the word right in front of it is the pattern we're looking for. So we're looking for the proton pattern. Anybody know what the proton pattern is in the periodic table? You can put it in chat. And the faster we do that, the faster we can get through this. So when we look at, so while I'm talking, y'all can put what you think the proton trend is for the periodic table. All right, so what I'm showing you here are the Bohr models. The Bohr models, we know the Bohr models are not the model of the atom that we believe to be now, but the Bohr model helps our minds and helps us understand things better than the electron cloud model. So just so you know, I'm showing you the Bohr model, but that's not what we believe the electrons circle in around the nucleus, right? They don't circle in these concentric rings, these circles, all right? Okay, but what was true about the Bohr model is that different electrons have different energies, and that's what these rings show, that the ones closer to the electrons closer to the nucleus have less energy than the ones farther out from the nucleus. Nice. And why do we need so many rings? Well, they have different energies. And the spaces around the nucleus get filled up because these electrons are all the same charge. Okay? Same charges repel, right? So they repel each other. So there's only so many of the same charges you could put in a space around the nucleus before you need to go out from the nucleus. So every time we add electrons in a new energy level, we're going more distant from the nucleus. Okay? So you are all correct. The pattern for protons is increasing. So that's one of the ways the periodic table is set up, is that every time you go to a new element, as you go from left to right across the periodic table, you are adding protons. Every new box in the periodic table adds one proton and it adds one electron. Now neutrons, we could add 3, 4, or 10, okay? But the pattern is increasing protons. Increasing protons across the period. The periods are rows and down groups.
You're probably not going to do very well.
Okay. So as you go across the period, it's one at a time. We add one at a time. Going down, you add more. For reasons to come. Now, next one, valence electrons. You guys have got to know what a valence electron is. If you know what a valence electron is, you can chat. The trend is increasing across the period and down a group stays the same. How many? Okay, so Melina, I am going to get to your question in a minute, okay? Because I'm going to get to energy levels in a second. All right, valence electrons are the electrons on the outermost energy level. So that's the outermost circle, the circle that's most distance from the nucleus, okay? So if we look at lithium there, we have a 3+ in the middle, then we've got 2 rings. The 2 rings means energy levels. The first energy level, though, what's closest to the nucleus, is the least energetic. So those electrons have the smallest energy. So that's what we call the inner electrons, because there's an outer electrons. I should have my phone off. I should have my phone off. I'm sorry. The outer electron shell is, or energy level electron shell, it's the same thing. That vocabulary means the same thing. So the outer one, the one most distant, the one in lithium, it's 1 energy level, or 1 electron in that energy level. That's 1 valence electron. So the electron in the outer energy level, that's the valence. You've got to know that. We're not only going to use that in this unit, we're going to use it in the next unit. So bonding, that's going to be really, really important. So you got to know the valence electrons. So that increases across the period. We add one every time we go across. Okay, so why, when we're going across, we increase, but then down here, it stays the same. That doesn't make any sense, right? Because we increase until that energy level can't hold any more electrons, and then we've got to add an energy level. So every time we stop a row and start a new row, we're starting over at 1. So if we look at lithium, that's 1. And then we increase, beryllium's got 2, boron's got 3, until we get to neon, which has 8. 8 is the max energy level. 8 is the max electrons for that energy level. So how many ever elements are in a period, that means how many electrons can be in that energy level. So each row is a new energy level for an atom. Okay. All right. So it stays the same because we start over at a new energy level. So down a group, it stays the same, the amount of valence electrons. So as you go across the groups, each group has a certain number of valence electrons. And that's going to be really important when we look at ions, which is next after trends. So the first group, hydrogen, lithium, sodium, potassium, all have 1 valence electron. This is why they're all in this group. It's the reason why they're all stacked on top of each other is because they also have the same characteristics. And they have the same characteristics because they all have 1 valence electron. Those electrons are the workhorses of the atom. They do everything. The bonding, how the element reacts, everything. All right. So now to energy levels. All right, so energy levels, the rings. Well, you can see that the rings increase as you go down. And I just explained this, right? Because every time we go across, we're adding to the same energy level. We don't get a new energy level until we go to a new row. So it increases as we go down and stays the same as we go across because we're filling that energy level as we go across. Now, Melina asked me a question. All right, Melina, that is a really interesting question. How many energy levels can you have around an atom? That is a very interesting question because what these energy levels are just shapes where the electron is most likely to be found. So like the first energy level is like a sphere. And the second one's like a dumbbell. The third, and it gets crazier from there. Okay, so to answer Melina's question, it's 7 because the number of rows in the periodic table is 7, and that's how many energy levels we can have. Good question. Good question. All right. Do we have any question on that slide? All right. So I'm going to talk about what the trends are right here. And later I'm going to tell you why they are what they are. Okay. So hang with me here. Atomic radius. Atomic radius is how big the atom is. That's all we're saying. We're saying the size. Okay, so it's the distance from the nucleus to the outer orbitals. All right, that's the size we're talking about. So basically the diameter, right? Not the radius. I think I just said those right. My husband over there will correct me in a second if I didn't. So the distance. So the distance increases as we go down, which makes sense because we're increasing energy levels and they get more and more distance from the nucleus. So that makes sense that those increase. Now we're going to look at the reason why later. And it's not just that we're adding more shells. That's part of it, but not all of it. All right. So, and the atomic radius increases as you go from right to left. Now, I always think of trends when we think about a group. I always think left to right myself. And I always think of from top to bottom. But it's easier, I guess, to learn trends if you always think of them as increasing. So then you just got to figure out which way they're increasing and learn from there. Okay. So this little picture shows increasing from right to left, which is true because as you go down a group, those get smaller for reasons we're going to see in a second. All right. Ionic radius. That's how big the ion is. Same as atomic radius, right? So when an ion is formed, a positive ion, that's what we call a cation ion. All right, cats are positive. That's how I remember that. Cation ion, the ion actually is smaller than the atom, so it gets smaller, which makes sense because it lost an electron, right? All right, and so if we have an anion, which is a negative ion, it actually gains an electron and it gets bigger. So that actually makes sense, right? So electronegativity, what that is kind of a made-up value is what that is. But it's made up so that we'll understand this process. So when we get to bonding, non-metals bond together and they share their electrons. And so what electronegativity is, it's the ability of one atom's nucleus to pull the electrons from another atom more towards itself. So it's like a tug of war. So if you think of both, if we're thinking of two atoms and we think of both nucleuses pulling at the electrons as the rope, this is a tug of war, one is going to win. And that's what electronegativity. So the higher the electronegativity, the more one nucleus is going to pull harder on that tug of war. So that's electronegativity. So it's the ability to attract the electrons from another atom. All right, ionization energy, our last trend. This ionization energy is not the energy it takes to make an ion. That's not what that is. That seems like that's what that is, but that's not what that is. Because some ions are formed by gaining electrons, and that's not what this energy is. All of this is the ability to pull an electron away from an atom. No matter what atom it is, okay, just how hard it is to take an electron away. That's all that is. So it's harder to take an electron away from some of them than others because some of them, the metals, want to give up an electron, and so their ionization energy is lower than the non-metals who don't want to give up any, right? So ionization energy. All right, do we have any questions on that screen? Okay, we're about to go into why we have these trends. All right. Maybe if I click on it. All right, so Chandler talked about Coulomb's law, and that's your two assignments in Go Formative on Buzz, but filled out in Go Formative. Okay, so what Coulomb's law says, and this is named after a dude, and so I always say when you find something new in science, you can name it after yourself too. Coulomb's law is about attraction. It's about electrostatic attraction between particles. And I just threw a whole bunch of sciencey words out there, didn't I? But you know what electrostatic attraction is, okay? It's the positive and negative charges. You know that, right? You know that because why? Opposites what? Okay? Opposites attract, right? And that's what we're talking about. The protons are the positive and the electrons are the negative. So that's what electrostatic is. The attraction will be positive and negative, right? Opposites attract. That's all we're talking about. Science likes to give everything a name. So don't be fooled by those sciencey names, okay? They probably don't mean that much, all right? So Coulomb's law says, when we talk about this attraction between positive and negative, there are some things that cause it to be more of a force between those two and less of a force between those two. So distance. Distance is one of those things that decreases the attraction. The more distance, the less force. You know this. If you've ever done magnets, so small little magnets, right? When they're attracted to each other, when they stick together, right? When we pull those apart, you can feel it's harder to pull those apart, right? That's that attraction. But the farther you get them apart, then you don't feel that attraction, right? More distance, less attraction. That's the first part of Coulomb's law. Second part of Coulomb's law is the amount of plus and negative charge, positive and negative charges. So the more charges we have, the more attraction. So this makes sense. If you got little bitty magnets, you don't have that many charges, and so it's easier to pull them apart. But if we got really big magnets, there'd be a lot of charges, and it'd be really a lot harder to pull them apart. More charges, more attraction. Those are the two things of Coulomb's law, and they explain most of our trends in the periodic table. So that's why we study them now. All right, do we have any questions on that? Do we have any questions? All right, so something that affects Coulomb's law. Now, Coulomb's law is true across the board, okay? But something that could also decrease the attraction is this shielding effect, okay? So if you look at my graphic here, all the positive charges are in the nucleus, and then you've got all these electrons out here, right, roaming around. Electrons are always moving. They are never still, always moving. So you've got inner electrons and outer electrons. So the electrons that get between the nucleus and the outer electrons do this shielding effect. The outer electrons cannot feel the attraction the nucleus is putting on the electrons. The inner electrons feel it more. If you could feel a force, okay, they don't really have feelings or nerves or anything like that, but they feel a stronger attraction. But these outer electrons don't feel the same attraction as those inner ones because those inner ones are pushing them away. So the attraction that they feel, the force on those outer electrons, isn't as much because you've got this shielding effect going on. And when we get to a trend that's kind of wonky or it shouldn't be as big as it is, which is really something that we would do, if, say, the distance, if we have like Coulomb's law and the distance should only allow the electron to be so far out, but it's actually more, that's when we have the shielding effect. We've got extra on top of Coulomb's law is basically what it is. All right, so this shielding effect, the way that we kind of measure it or kind of just give it a number, this is a made-up number again, is the effective nuclear charge. Now, Buzz taught you this instead of teaching you Coulomb's law. I think Coulomb's law is far more important to periodic trends than Buzz taught you, so that's why I'm teaching you this now. So the effective nuclear force is that extra shielding effect that comes into play. And so there will be one question on your test about calculating the effective nuclear force. And the way that Buzz had explained it to you is the number of protons minus the number of inner electrons. I think that's a dumb way of calculating that. I don't even think you need to calculate it because I think this is far more effective right there. Because if we subtract the number of protons and the number of electrons, what do we get? We get the number of valence electrons. So as long as you know the valence electrons, you don't have to do that protons minus electron stuff. So the effective nuclear force is really just always the amount of valence electrons. Okay, so that changes across a group. That doesn't change down a group because the valence electrons never change down a group. But across a period is, so really the effective nuclear charge we could really only talk about across a period. Okay, all right. So if we look across a period, if we look on the left-hand side of the periodic table, the effective nuclear force is small, 1, 2, because that's how many valence electrons we have here. So the shielding effect actually is greater over here. Over here, we get a higher effective nuclear force because we're going to have more valence electrons. So if you're talking about effective nuclear charge, it's how much force the nucleus is put on the electron. All right, so a higher effective nuclear charge, it means there's a more attraction. So a higher number, more attraction that the nucleus is putting on the electrons. All right. All right, any questions about that? You may not get questions until you start doing your homework or quiz. So, you know, you can always email me and always know you can get on at this time and get questions. All right, we're going to go over 5 trends and then we're going to be done and I'm going to have you do your signature and you're going to be good to go. So we're almost done, all right? So, atomic radius. I told you what it was earlier. Now we're going to say what the trend is, okay? I guess we alluded to it, but now we're going to say why the trend is. So atomic radius is how big the atom is, and as we know, it increases down a group. Why does it increase down a group? Well, because we're adding energy levels. And it's more than just adding energy levels, it's Coulomb's law is getting weaker, or sorry, Coulombic attraction is getting weaker because we get more energy levels more distant away from the nucleus. So more attraction. I'm sorry, less attraction. I should have said more distance, less attraction. So that's why the atomic radius gets bigger down a group, more distance, less attraction. You get more distance because they're adding energy levels. So more distance, less attraction allows those electrons to pull to get farther away from the nucleus. Now, across a period. Across a period, we are not adding energy levels. Energy levels are added every time we go down a row. But going across the row, we're just adding electrons. And so this is the other part of Coulomb's law where we're adding more charge. We are not adding distance. So we're just adding more charge. So more charge, more attraction. So what happens across the period is we're getting more and more charges, we're getting more and more attraction, so the nucleus can pull those electrons in tighter to itself. So this is like Spanx in girls. Not that any of y'all need them. You need old women like me, need them. Or compression shorts for guys. This is my analogy. All right, do we have any questions on why we have these trends? Okay, we're going to go to electronegativity. Now remember, electronegativity is the ability of a nucleus to pull electrons towards it, not its own electrons from other atoms. So it decreases across down a group. Well, your Coulombic attraction decreases. So if the outer electrons aren't feeling the full force of the nucleus, then how are other electrons from other atoms going to feel it, right? So more distance, less attraction. See how Coulombic attraction comes down there, all of these. All right, so electronegativity across the period increases because the attraction of the nucleus increases. More charges, more attraction. Okay, so the effective nuclear charge goes up, so that means more force can pull electrons from other atoms towards a nucleus. Okay, we have any question on that? And sometimes I know you have to type it in, so I might go past it and I'll come back to it. All right. Ionization energy. Ionization energy is, remember, not the energy to make it an ion. This is how much energy is to take an electron away. So that decreases down a group. Why? Because the more distance, less attraction. If the nucleus has less attraction on the outer electrons, it's easier to pull those electrons off, right? So across a period, it increases. It's harder to take those electrons away because there's more charges, more force. It's harder to take something away from the nucleus because it's holding on so much tighter to its electrons. So Coulombic attraction effective all the way here. All right. All right. Also, across a period, you don't increase the shielding effect. The shielding effect is constant across the period. So if it's constant across the period, the effective nuclear charge actually goes up because you're adding electrons, so the effective nuclear charge is going up. And so more particles, more force. All right. Ionic radius. So this is a hard one, and it's really hard to put it into a trend because you can really only look at it for the metals and for the non-metals. You really can't say that there's a trend from metal to non-metal. You can't, because it changes, because as we saw in the previous slide, forming a cation, a positive ion, which just takes the electron away, which is the metals. That's going to be good for the next unit. It decreases, right? So that means everything on this side of the periodic table, which, I'm sorry, here. This side of the periodic table decreases as it becomes an ion. So this is getting smaller. But over here on this side in the non-metals, they're getting bigger because they're forming anions. So you can't say these are getting bigger or these are getting smaller than these are getting bigger. And so it doesn't really relate all the way across the period in a group. Okay, I'm going to show you a little. All right, so these are ions. Let me blow them up a little bit here so you can see them. So the gray is the neutral atom, and then the colored ones are the ions. So you see the metals, which are all these green ones, are getting smaller. And then these over here are non-metals. They're the purple ones, and they're getting bigger. So I know these numbers really don't mean anything to you, and you can't really see their number, but really what's happening is this number right here is for the ion, and it's bigger than any of these numbers. So really you can't say that this is a trend across the entire period, but you can say it's a trend within the group. So the metals and the non-metals, we can say there's a trend. So in the metals, it decreases across the period, and in the non-metals, it increases or it decreases across the period. All right, so that slide back on their notes is a little deceiving And really, there aren't going to be that many questions on your test about this, but in general, this is how this goes. And it has to do with the Coulombic effect. If you take an electron off, that makes sense that it's going to decrease in size, right? And if you put an electron on, that makes sense that it's going to increase in size, except for the Coulombic effect, because if we add particles, it should make it smaller, right? Ionic radius really kind of throws us off. So there's not gonna be a whole lot on your test about that. All right, we're gonna go through one more trend and then we're gonna be done. Woo, holler. All right, reactivity trend. So this is important. Well, A, because we study elements because they do react with one another. If atoms didn't combine with other atoms, there would only be 118 things in the entire universe, and you and I would not be one of them. We are here and made up of compounds, which is atoms bonding with other atoms. So this is really important when we get to bonding, okay? So metals act differently than non-metals. So we have to break this trend up too, kind of like we had to do for the atomic radius. So the trend in metals is it increases as we go down a group and it decreases as we go across the group. So if we were looking back, and I don't really want to do that for you because those of you who are writing this down, remember we add valence electrons as we go across, right? And what do metals do? Metals allow those electrons to be taken from them. So as we gain more electrons, it's less reactive because it's harder and harder to get rid of those electrons. Coulombic force, right? So that's why over here, the alkali metals, which was on your last test for some of you, alkali or noble gases was on your last test. Alkalis, they're very reactive. You rarely find them in nature because they're so reactive and they're always bonded to something else just to be stable. All right, so decreases this way, increases, decreases across the group, across the period, decreases down the group. All right, now non-metals over here. Non-metals going across become more reactive. Okay, more reactive. So you see metals became less, but non-metals become more. So we can't look at them together, right? All right, and then down a group, they become less reactive. It decreases because the nucleus is so far from the outer parts of the atom that they can't bring in other atoms. So the non-metals, they get together and they share. They share electrons or they take electrons away from metals. All right, this is our trends. Do we have any questions? Put questions in chat. Otherwise, we're going to go do our signature and then we're going to be done. I know that was a lot of information. I just kind of threw it all at you. Hopefully that all made sense. When you do your assignments this week, it's going to make more sense. And then hopefully it'll make perfect sense by the time you get to your test, right? All right, the last thing I want you to do, and some of you may have already done this, if you're supposed to do this in your advisory. And so what I have found that this really, really helps me. When you send me an email, I don't have to go look at all my lists and see which class you're in and then figure out from your email where I need to get in Buzz and all that. If you put your schedule in your email, that helps all your teachers. So I want you to do that right now. These are the instructions. If you have already done this, because you were supposed to do this in advisory a week and a half ago. If you've already done this, send me an email and I will see your signature there and you'll be good to go. If you have not done this, this is the way this goes. Actually, I found an actual easier way. Let me just see. Oh, my Gmail is not responding.
Don't,
Yeah. Okay, so what you do is you go to the right-hand corner. Over there is the settings. It's the gear-looking icon. You click on that, and then you'll have to click See All Settings, which I can't right now because Gmail won't let me. But after you see All Settings, you'll be in General, and then you scroll down to Signature, and then you're going to do this. So you're going to create new signature. Then in the left-hand box, you're going to give it a title. And then in the right-hand box, what you're going to put is your name, your campus, and your entire schedule. And I don't want to know what classes you have. I want to know when you have these classes, right? I know you have chemistry, but tell me when you have chemistry. That's what I need to know. All right, so after that, and this is really important, be sure to, underneath, when it says signature defaults, click on the down arrow and pick whatever title you gave your signature. And then be sure to save. Then you'll be done. Send me an email, and then I'll tell you whether you're good to go or not. All right. All right. Some of you may have already done this. So
this one was
just send me an email.
family in here. I'm gonna look at it, leave class if you like, or if you like to stay. Questions, I am certainly available. I am here.
I'm wondering. Has anybody sent me an email? Because I'm wondering if it's working right. Okay. Okay. This is bad. My Gmail is not. Let me get out of my Gmail. Maybe there's a problem with Google. Maybe there's a problem with the internet. There's a problem with Gmail. I can't even get onto my Gmail. Dope. All right, so since I can't get onto my Gmail, I want you all to do this and send me an email. And then you can go. If you didn't set it up right, then I'll have to send you an email back saying, hey, I think you forgot something. But otherwise, you're good to go. Be sure to do your signature. And I don't know if Miss G needs anybody. Do you need anybody to stay, Miss G? Miss G, do you need anybody to stay?
I have people scheduled for Flex. If somebody needs to come to Flex, please tell me now. There's some of you that may like to, and you're welcome to. Just let me know and I'll pop your name into my Flex.
Yes, also, if you need me in Flex, in our Google Classroom, in the stream, I've put a Flex Google Meet. So you can get me anytime during Flex. All right, just go to your Google Classroom, go to stream. Not this Google Meet, a different Google Meet, right? Don't use the one at the top of the page.
Yeah.
Look at the one in the stream.
And for me, I'll send you an email with the correct one because I have several different kids coming to join me at different times. So, and there's just a couple of you that I would like to, but I didn't see them on our list as here today. So there we go. So if you want to, let me know.
All right. As soon as you send me an email, normally I would check it and then say you're good to go, but my Gmail is down.
Oh.
So once you send me an email, you can leave.
And Malia, did you want to come to Flex or were you just answering a question with the yes?
I got out of my Gmail and it says I can't even reach that site.
Wow.
I wonder if it's down everywhere.
That seems a bit rude.
Well, my husband says he's got his. Is it open? Doesn't mean you're getting new emails.
I'm gonna see if I can
No.
update mine. It doesn't say I can't.
My last one's at 9:53.
Oh.
Yeah, I can access mine, it seems like. So
I don't know. I don't know what's wrong with mine.
you're just broken. You're broken. Melina, do you want to join me in one of my Google Meets? One of my Flex
I'm looking at
meets?
this.
You do? I'll send you an invite, Melina, and then if you don't want to come, you don't have to. Miss Brock, I can't get on my Google Calendar, so there's apparently something going on, I'd say.
Oh, interesting. Okay. That's
Yeah.
good to know.
Yeah, it doesn't make it very handy for Flex Meets. But we'll see what
Yeah.
happens. Maybe it'll be up and running in a few minutes.